Yeah, well, I've been having some problems with the internet connection today. I mean, I'm using Ethernet, so I'm plugged like right in with a wire. But like when I was streaming class this morning, it was like really laggy. So I've been going back and forth today trying to fix the stream quality. But I don't know, I'm looking at some of the settings right now and it feels like it's still not in the best shape. So weird. How does the stream quality look for you guys right now? Is it kind of laggy? Is it freezing? Or is it kind of normal? I noticed some laggy bits last stream, but so far so good. A little choppy today. Yeah, I think the same thing was happening on Friday, now that I'm thinking about it. Because the Streamlabs software that I'm using, it was giving me some warnings, even on Friday. And I don't know what it is. Like, I don't think the upload speed is too bad. Like, I just did this speed test and it's like 6.6 megabits upload, which is okay. Yeah, you noticed it on Friday too? I don't know. No, it wasn't just you. It wasn't just you. I think it was happening for everybody. Ugh. But what we're gonna do, today's gonna be a little shorter anyways. I think we're just gonna try to blast through this, and I'll keep working on trying to figure out what the problem is here. I do not know what it is. Okay. Hope you guys had a good weekend. I hope you had a spooky Halloween. Hey, UB Math Prof. So now that you're here, have UB Math Prof, have you had problems with dropping frames recently? Like starting on Friday, my stream has gotten like really choppy, and I'm still trying to figure out what's going on. Oh, you're having problems too? Is it just Twitch, or what's going on? Are you having problems this week too? Oh, you won't know until tomorrow. Yeah, I don't know. It seems okay now. Okay. It kind of ebbs and flows. This morning it was really bad. Yeah, it's probably spiking now, right? Well, okay, if you're just joining, for some reason the stream quality is kind of poor, but I'm going to try to push through, finish this set of notes, and then hopefully come Wednesday there's going to be some resolution to it. We'll see, but we'll hang in there, we'll push through. Okay, so we are talking about lateral flight dynamics, and I just kind of want to walk through a little bit of what we did last Friday. So to define lateral flight dynamics, it's basically a combination of yaw and roll motion. So yaw is spinning about the z-axis that's pointing right out of the bottom of the aircraft. So think about just spinning like a top. Rolling is spinning about the body longitudinal axis. And I think we have a good idea of what rolling looks like. So lateral flight dynamics, there can be combinations of yaw and roll, and there's some pretty interesting modes. And Wednesday, I want to get into the detail of these modes, what they look like. But today we're just going to mathematically derive that they exist, and we'll when we talked about longitudinal modes, we looked at the Boeing 747. I want to do the same thing with lateral modes. So we'll look at the 747 again today. We'll go into Matlab and work with that. So reviewing a little bit, we talked about how how a pilot can introduce yaw and roll motion. Oh boy, stream is unhappy. Yeah. No, it's not just you. It's not just you. So if any of you guys are noticing that the stream is kind of dropping frames, it's not you. And I don't even think it's me. I feel like there's some problems with Twitch recently. I don't know what it is, but I hope it resolves soon. So just hang in there for today. Lecture won't be super long anyways. Okay, so we talked a little bit about the rudder. So if you have the tail of the aircraft, the rudder is that vertical tail that directs from side to side. And we looked at a case of positive rudder deflection. Maybe there's a Fortnite tournament. Oh, it kind of cuts entirely and goes to a loading screen every half minute. Ugh. Well, okay, we'll keep going. Tell me if it gets to a point where it's totally undoable, or it's just not going to work at all. If it's totally too distracting. Maybe there's a Fortnite tournament eating the bandwidth. Yeah, I don't know. Maybe Twitch finally reached its bandwidth. That's hard to believe. Okay. But what's shown here is positive rudder deflection, and that's going to yaw this aircraft. It's going to kind of swing the nose around to the left, and that's a negative yaw moment. And yaw, the rudder, it doesn't just yaw the aircraft about the z-axis. If we look at the aircraft from the front and we see that the rudder's deflected over this way, I just popped in some other streams and they're experiencing the same thing. Okay. Well, that's good to know. That's good to know. I was worried that it was like just me, but yeah, hopefully this gets resolved soon, because Twitch is really popular, so I bet they're working behind the scenes, but we'll figure something out. We'll just get through it today. But, okay, anyways, the rudder, it is a vertical distance from the CG of the aircraft. So when I deflect the rudder, it generates a lateral force this way. And because that lateral force is acting some distance from the CG, it also creates a roll moment. If I come back and watch the recording, will it still skip? I think that it'll have some skips, but I don't think it'll have loading screens in between. I think that the audio will be pretty consistent. I think that the image will still jump around a little bit, but it might be more tolerable to watch after the fact. I'm not saying leave, but I mean, being realistic, it might be a smoother viewing experience after. Not gonna lie. Okay, so if you deflect the rudder, it'll yaw the aircraft. It'll also roll the aircraft. Okay. So I don't want to spend too much time on this. We'll just review this, and I know it's lagging, so I kind of just want to finish up this note set. And okay, so the rudder is one of the control surfaces that creates yaw and roll, but the aileron or ailerons also create roll. And so these ailerons are little tabs on the close to the wing tips, and what I'm showing here is considered positive aileron deflection. So this flap to the, or this aileron, sorry, to the pilot's right hand side, it goes up, and this aileron to the pilot's left hand side, that goes down. That results in a decrease in lift on the right wing, an increase in lift on this wing to the pilot's left, and that causes the aircraft to roll in this fashion. So just an intuitive explanation, ailerons create that roll motion. They're in fact the primary control surface to create roll. Okay. And we also looked at what happens to an aircraft when you start to roll it, and there's two main features. I think this picture is most indicative of what happens. So most aircraft will re-stabilize when you induce roll, but what's going to happen is, let's say, so I'm looking at an aircraft from the rear here, and it banks a little bit to the right. So this is a positive roll angle. What's going to happen is it's going to lose a little bit of altitude, and because of what we call the dihedral moment, there's going to be, well, let's talk about it more intuitively. When you start to roll, you lose altitude, and then the aircraft starts moving to the right, in this case, and that creates airflow from the side, or a relative velocity from the side. And depending on the dihedral moment, the aircraft corrects itself and kind of flattens out from that roll. This is an example of what would happen to an aircraft if it didn't stabilize itself in roll. It would just continue tipping over, and that's no bueno. One of the ways that we help deal with this is the dihedral angle. So if the wings are kind of pitched up a little bit in this fashion, it makes it a little more stable in roll. Okay, so we're just walking back through that. I wanted to reintroduce that. So the way we define lateral flight dynamics is we take an aircraft flying straight, and then we perturb it a little bit, maybe hit it with a gust of wind. And what you can do is, in the linearized dynamics, you can find 4 of our aircraft states that are interdependent on each other. We have this lateral velocity. We have a roll rate. Stream actually just cleared up on mobile. Oh, nice. Okay, that's good to know. Yeah, maybe you could see if it works a little better on your phone. Looks okay on browser too. Okay, good. Maybe it's getting a little better. Okay, so we have, what else do we have? This is our yaw rate, and this is a roll angle. So we pull out these 4 states, and when we linearize our dynamics about just flying straight, then these states are interdependent, and we call those the lateral dynamics. Slight desync on audio and video on desktop for Bane. Okay. Well, I'm happy it's not just terribly distracting. Okay. So, we'll get to these modes. Spiral mode, roll mode, Dutch roll mode. We'll come back to these. Okay, so these are our 4 nonlinear equations, which we're going to linearize about just a flying straight reference condition. That's going to give us our lateral flight dynamics. And we started doing this last time. This equation, it's on your most recent homework, but let's fill in the main result here. You should get this for this linearized equation. Delta V dot is YV delta V plus W star plus YP delta P. And I think this W star, generally people set it to 0 for this reference flight condition. So we'll just do that. Y sub R minus U star delta R plus G cosine theta star delta phi. And one more term, which I didn't fit in the box. Plus Y sub delta R delta R. Okay, so this is going to be the perturbation dynamics for our lateral velocity. Delta V. Okay. And the way to get from up here to down here, let me just sketch it out, even though I won't do all of it here, of course. What you do, if we call this right-hand side, I don't know, a function f, then we do our Taylor series expansion here, df dp delta p So you do this expansion with respect to all of the variables that appear in this equation. df. And this star here just means to evaluate that partial derivative at the reference flight condition. And for the reference flight condition, most of these parameters are set equal to 0. And then it just goes on. You just cycle through. So like I did P, W, R, then you got to do U, you got to do phi, theta, and Y. And that's how I got this down here. Okay. We're going to keep moving along. So this is our first linearized equation. This one we did last time, delta P. This is a little bit of a longer expression. But this is our dynamics for our roll moment. Just keep moving along. And then we linearize this R dot equation and we get delta R. Where did Y sub V del V come from? Chat is still slow. Oh, sorry. This one? Okay, where did that come from? Because, so if I keep continuing this expansion up here, I'm going to get to a point where I differentiate with respect to big Y. And I multiply by delta Y. Now, if we look at this term, df dy, so if we differentiate this with respect to big Y, that's just going to be 1 over m, right? Now, we're multiplying by delta Y. And if you go up here a little bit in the notes, we talk about what delta Y is. So this is delta Y. So back in that expression down there, you have to substitute this. So we go back down here, sub in delta Y from above. And when you do that, this is one of the terms you end up with. I mean, that's where you also get this term, and this term. Okay. Okay, delta R. This one I'm just showing you what it is. And then this next one we're going to go through in detail. Okay, so we'll do delta phi. Yep. It expands into those new terms. You probably typed that a while ago. But there's some lag. Okay, so I'm gonna first differentiate this with respect to P. Actually, let's do this. Let's do this the long way. I'm gonna call this F. We'll do that. Let's see, df, dq. All right, so that's the general Taylor series expansion. Yeah, lag is real. What a bummer, man. It's more fun when it's like, you know, responsive and snappy. But we got probably like a minute of delay here. Not cool. Okay, if we differentiate with respect to P, we're going to get delta P. Oh. Yeah, I turned off link sharing. All right, if we differentiate here with respect to phi, from this first term, the sine becomes a cosine, and I have to evaluate this at the reference flight condition. And then I'm also going to differentiate this term over here, so that cosine phi is going to become a sine. All right. Now let's differentiate with respect to theta. So the derivative of tan theta is 1 over cosine squared theta. Probably been a while since you've done the derivative of a tangent. One over cosine squared of theta. Okay, so we're up through delta theta. Let's do Q. And finally R. There, we did it. Now, let's substitute in some of the things from the reference flight condition, and a lot of these terms are just going to disappear. So, for example, our reference flight condition is non-turning. So that means my... that's my pitch rate, right? Q. Q is the pitch rate. That's 0. R is the nominal yaw rate. That's 0. So our reference flight condition, it's not turning. So all of these turning, these angular velocity terms, they go to 0. Our roll angle is 0. So this sine of phi, that goes to 0. This cosine phi goes to 1. So a lot of this stuff went away. So this is just going to boil down to delta phi dot is delta P. This went away, this went away, this went away, and all we have is tangent of our nominal pitch angle, whatever that is, times delta R. So this linearized equation is nice and kind of cute compared to our other ones. Thank goodness. All right, so what we're going to do now, we're going to gather all these terms in state space form, and I already filled in 2 rows of this. So we're going to fill in the other 2 rows. And I'm realizing it'll be a little hard to do this. Let's do this delta phi first, because that one's easy. So phi dot, it's delta P. So what I should have is 0 times delta V plus 1 times delta P for this delta phi dot row. And then I also depend on delta R. It's going to be the tangent of theta dot. So I got to take tangent, or yeah, just tangent of theta times R, and then a 0 here. So this matrix, this is a state space form. This is going to be our A matrix. I don't know, maybe we'll call it like A lat. It's for lateral dynamics. And when we do state space form, we also have a corresponding B matrix, which is for our control inputs. So like this matrix, we could call it B lat. So this this 4th row here, which I left empty, would correspond to delta phi. And delta phi dot didn't depend on these control inputs directly, so these 2 elements of the B matrix would be 0. Okay, so that's our easier 4th row. Now, filling in this delta P dot row, a little more work. Let's go back, go and look back at delta P dot really quick. Okay, so the first term we're going to work with in our matrix is the coefficient of delta V. So it's going to be like LV star plus NV star times this stuff. And there's actually a little pattern to this. Because it's going to look like this 3rd row a lot, except that the terms are just kind of switched. So this first element is multiplying with delta V. So it's going to be LV star times delta V plus this ratio of moments of inertia times NV star. And if you compare to the row below, it turns out that all of these terms just have like the LVs and NVs interchanged if you were to look at the equation above. And so we'll just kind of take a shortcut here, knowing that this is what we would find anyways. Okay, IZZ and R. And then this last element in the row is also 0. Okay. And we have completed the A matrix for lateral dynamics of an aircraft. Okay, let's finish populating the B matrix then. And this same trend that we had in the A matrix, it happens for the B matrix as well, where it looks the second row looks the same as the third row, but some terms are interchanged. So we're going to do that here. So instead of leading off with the N term, we're leading off with L. And we still have this same ratio of inertias, but now it's multiplied with this N term. I keep saying L and N, but physically the L is the roll moment, N is the yaw moment. So okay. Okay, so what we're going to do next. We have successfully linearized the lateral dynamics equations about a reference flight condition, just flying straight. What I want to do is I want to create this matrix for a Boeing 747. Because we have these parameters, you can look them up. And I happen to have a textbook that has all of these stats on the 747, and it's cool now that to have these general equations, because you can apply them to any aircraft. So if you have these stability derivatives for an F-16, whatever, you can get those lateral dynamics for that aircraft. So you only have to derive these once, and then they're good for analyzing a lot of different aircraft. Okay, so I'm going to go over to Matlab, and I'm going to show you a code. As a side note, I hope you guys are doing well. End of the semester always gets stressful. Everybody's tired out. Yes, even you can admit it. And just know it's okay. Just keep putting one foot in front of the other. Make sure to not be alone. Talk to some friends. Get some encouragement. Get some rest. Build some healthy routines into your life. Okay. This is the weight of a 747 Boeing. 636,636 pound force. And didn't we have a debate about what a scale actually tells you, if it's pound mass or pound force? It's pound force. Crispy Brownies says this semester feels a lot more difficult than the last. Yeah, I agree. Being remote brings a lot of new challenges, and it's isolating. There's less structure throughout your day, and structure is really, really helpful in school, just for pushing through something that's difficult. I know, heck, COVID. Yeah, COVID is really, really a bummer. Really a bummer, guys. I'm bummed that I can't see you guys in person. I know it affects your learning. It's affecting everybody. It's affecting your professors as well, guaranteed. When I talk to other professors, they're tired. And when we hear from students, they're tired. UBMAE student says it's kind of inhibited my learning, to be honest. Yeah. And classes got intense. Yeah. Man, it's just not cool. All right. So definitely wouldn't have interacted this much in person though, so it's good and bad. Yeah, I hear you. Like Twitch is fun because I think it's easier to interact, you know. In some ways, you can just throw stuff in the chat. It's just I don't know, it's kind of laid back. So it does have pluses and minuses. I've really enjoyed the interaction on Twitch. It's fun. It is fun. There's some silver lining. But all that to say, I wanted to just point out, I'm sure you guys are tired. And just, I want you to know that you're okay. Just keep going on. Keep pushing through. This isn't forever. It'll pass. Like a dream. It'll be gone. Just like a miracle, right? I don't mean that, but it will pass. Okay. Hey, thanks, Tim. I really appreciate that. Thanks, Jordy. Okay, so we got these inertias. These IX hat, all these, whatever. They're just these terms that we use to kind of simplify some expressions. So don't worry about this. This is just some inertia. This is how fast our 747 is going. I think it's like Mach 0.8. For this case, I'm going to assume that the nominal pitch angle, theta star, is 0. So all that means is that like the nose of the aircraft is kind of level with the Earth. Because we all know the Earth is flat. And so it's just level with a flat Earth. All right. Now these partial derivatives, these numbers, I grabbed them out of a textbook. They're right here in this table. But I mean, these kinds of, there's databases. So whether you find these in a textbook, a database, or something, just know that these numbers for different aircraft are out there. Okay. So these are just stability derivatives. LV star, LP star, LR star. That's all of this stuff. LV star, NV star, all of that. And I just got that. I got these numbers from that book. Okay. This is our A matrix. And I just typed it into Matlab in advance. You guys have no problem with this. And this is what I want to do. I want to get these eigenvalues of that lateral A matrix for the 747. Let's run this. I'm going to put whenever you put keyboard in your code, it'll just have Matlab stop at that line. Like if you don't want to run the whole code. So it's only going to run up to line 52 and then it's going to stop. Okay. So I want to get the eigenvalues of that A matrix, that's the same as the roots of the characteristic equation. Now, if you remember from the longitudinal dynamics, we got two pairs of complex conjugate roots. This is a little different. We get one pair of complex conjugate roots right here, and then we get two real distinct roots. And this actually constitutes three flight modes. This complex conjugate pair is the Dutch roll mode. This this one, minus 0.56, just a real root. This is the roll mode. And the reason I know that this one is the roll mode is because it's a faster route than this one. And if there wasn't so much chat lag, I would ask you how I know which one is faster. And the answer is a root is faster the more negative its real part is. So this is more into the negative than this one. So this minus 0.56 is a faster route, and the roll mode is a faster route than the final mode, which is the spiral mode. Okay, let's break this down. We're gonna go back. Okay, so we substituted parameters for the Boeing 747. We solved for the eigenvalues of the A matrix, yielding so I'm just gonna regurgitate those numbers here. Let's say lambda 1 and 2 minus 0.0337 plus or minus 0.9455i, and then lambda 3 minus 0.5606, just a real root, there's no imaginary part, and then lambda 4 is minus 0.0073. Okay, now we're going to write down the names of these modes. This is the Dutch roll mode. This is the roll mode. This is the spiral mode. Okay, and let's see where I want to go from here. Roll rate. All right, what I want to do, I want to give you a quick preview of these modes, okay? And then on Wednesday, I want to get into more detail on how you actually dissect these motions. So I'm going to come back over here. Let's talk about the spiral mode first. So there's two cases here of what this mode can look like if it's unstable. So for the 747, it was stable. Don't worry, you're safe flying. But let's say that we introduce a side slip disturbance. The way you can introduce a side slip disturbance is just hit the aircraft with a side gust of wind. That's all you got to do. Or you could tap the rudder. Boom. Okay, so we throw it off its like initial flight path by introducing some side velocity. Now, if you just leave the aircraft to itself and you don't do any corrective action, if it has directional divergence, which is a certain class of a spiral instability, the side slip will just keep growing. So it's kind of, eventually it's going to be spinning like a top, heading off here to the left. Okay? There's another type of motion, if it's unstable, called a spiral divergence. And this, it looks like a banked turn. So the aircraft's actually going to roll to its left. And it's not going to have hardly any side slip. So its nose is going to be pointing along this path, as you can see here. But what's happening is it's rolling. It's rolling. And so it's in a banked turn, and the spiral keeps tightening. And it's losing altitude. I wonder, actually, if there's a YouTube video of that. Probably be really, not good. This looks like just a UAV, so I'm not worried about a person getting hurt. Oh, here we go, here we go. He recovered from it. So we're banked. Banking to the left, losing altitude, but that quickly just went into like a nosedive there. And I guess that's where that spiral divergence heads eventually. Like you're... Interesting. I kind of want to check this out. I mean, I don't know if this is spiral divergence, but this is what I'm talking about. It starts like this, but the banked turn radius gets tighter and tighter, so it'll look kind of like a tornado. Okay. Okay, so that's the spiral mode if it's unstable. Let's go here. The roll mode is I guess what you'd expect. Like, you introduce a little bit of bank, and then what happens with the roll mode, this new flight sim has a full physics model, so I could actually attempt to record certain flight maneuvers. Dude, wait, which flight sim are you using? Or is it just called flight sim? That would be a really good tool to bring into this class. Okay, the roll mode. Well, let's look at this figure on the right. This P is the roll rate. So if I introduce a roll rate disturbance, the rate will keep increasing to well, it kind of has this first order response where the roll rate eventually levels off. But like what it's going to look like is the aircraft is going to keep rotating about its nose, and but it's going to reach a fixed rate of rolling. So it'll be stable in that the roll rate stabilizes. It won't just like keep increasing faster and faster and faster and spinning. Okay, the most interesting though is the Dutch roll. And this is a head-on view. It involves some roll motion, some yaw motion, and a drop in altitude. And I actually generated this in Matlab with the 747. You can buy a stick and throttle after COVID, have a setup people can check out. Yeah. Yeah, we need a flight simulator is what we need. All right, let's go back to this. I want to show you a little animation I did for the Dutch roll. And then I think maybe Wednesday we'll be able to build this together or something. Oops. This is going a little fast, but maybe I can pull this around. But this is that Dutch roll trajectory. It goes like boom, boom. Maybe I can slow that down. Where are you? Do I want to do that? I want to make this a smaller number. Maybe I want to do this. To improve this animation, I need to not just use a dot. I need to do something that shows where the nose is pointed, like if the wings are tilted. That would be some next level animation. But I think you get the idea. Yeah, the aircraft is heading this direction and kind of doing something like this. And I think that's what the textbook is showing us here. Yeah, you're like looking down. And somebody said the Dutch roll was a... Oh yeah, it was one of you guys said the Dutch roll might have been an ice skating move. Kind of looks like a slalom kind of thing. Okay. But that's what I wanted to show you. I wanted to get that four-dimensional matrix. I wanted to get the eigenvalues for a 747. Tell you what the different modes are represented by that. And then give you the most basic idea of what each of them physically means. But next time, I want to get into more detail on that. I want to do it more justice. But thank you guys for persevering through a choppier stream. Hopefully it gets fixed. And in the meantime, just keep persevering. You guys are doing a great job. School is tough, but you guys are doing a great job. Oh, Dilly says, do you know what the average on the exam was? Yeah. Let me take a peek. Let me take a peek. I want to say it was like mid 80s, something like that. Hey, thank you, Tim. Okay, let's see. I'll just get the stats. Oh, okay, here we go. Hey, yeah, thanks. Hopefully, Twitch figures that out. Okay, the average score was 86. The median score was an 88. I thought it was pretty good. It seemed pretty solid. Is there going to be an answer key to the exam? I think what we're going to do is, yeah, I think we'll post an answer key on the box. I'm not 100% sure. I need to check with Dr. Lagore, but I think we're posting that answer key. So you'll be able to go back, see exactly. But yeah, I'm not 100%. Yeah, have a great day, Dilly. All right, my friends, I'm going to call it right there. Thank you once again.